Okay, hello biologists. Let's jump it back into our Hardy-Weinberg lab. I'm going to share my screen with you to the lab manual. So um, on page 38 and 39, it takes you into the Hardy-Weinberg equation, which it's kind of a strange way to do it. I do like this visualization of the P's and the Q's, like the Punnett square. And Bozeman Science has a fantastic video that walks you through that. So if you haven't seen that one already, I highly recommend that because it's a really great way of thinking about what Hardy-Weinberg is really trying to tell us. Okay, and then it gets into what can we actually use our spreadsheet for and what can we use it to tell us? And I also really like this paragraph right here about the idea that Hardy-Weinberg is the null model, right? In Hardy-Weinberg, nothing changes. And so it is a tool that we can use to come up with our null hypothesis. Because Hardy-Weinberg is assuming it has all these assumptions, right? It's assuming random mating, it's assuming infinitely large population or sufficiently large at least. It's assuming no migration and no natural selection. So it tells us what would happen if nothing was changing. And therefore, if what we see doesn't match Hardy-Weinberg, we know that something is happening and we can go figure out what that thing that's happening is. Okay, so now you're going to use it to ask your own scientific question. So I'm going to model my scientific question. Yours may be similar, yours may be different. There's a lot of different kinds of questions that we can ask here. And if you're having a hard time coming up with one, reach out to me, let me know, and I'll probably give you some ideas at some point as we go through this right here. And then the data collection is a little bit tricky and the data visualization is a little bit tricky. So we'll take some time going through all these steps. This will probably be a handful more videos. Okay, so I'm going to share to my Excel document, which at the end of the day yesterday looked like this. It has 5 generations and each generation has approximately 100-ish individuals. And I have these little graphs that tell me their genotype. And every time I hit F9, it all changes. Okay, so there's a lot of different ways to model violations of Hardy-Weinberg, and one we can do is natural selection. And natural selection just means that some of our individuals, some genotypes, are not random, but some genotypes are going to be better able to survive and reproduce than others. And that is what I'm going to model for mine. Other things that we can model is we can look at the effective population size and run the model with different population sizes. Some students like to try and figure out if they can totally get rid of an allele. Bottlenecks, that's another fairly easy one to model. Migration is a little bit trickier, but it can be done. So yeah, there's a bunch of different things that we can model. I'm not super happy with only having 100 individuals in my population. I'm going to try and bump this up a little bit more. So I'm going to highlight a chunk and then I'm going to go insert. And I'm going to do it again, insert. 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 Yeah, okay, I messed up. Okay, I'm gonna stop there. Okay, and I'm gonna highlight all these. Oh, my mouse has been like such a problem today. Okay, fine. I'll just do one generation at a time because it's not letting me highlight like all the way to the right stupidly. Okay, scroll down. Ooh, I inserted a whole bunch. Yay. Where'd they go? Okay, so I'm going to be at like 250 individuals in my population. And so as I drag these down, okay, I wonder if I can just make this really small and do a whole bunch of it at one time. Okay, there we go. Mouse, you can do it. Make it all the way to the end. Okay, now I'm going to do all these guys at the same time. Okay. So right now my spreadsheet is set up for 5 generations, but I know that after that 5th generation, it was pretty darn easy. I mean, after adding that 2nd generation, it was pretty darn easy to add another generation. So what I am going to do is I'm going to copy a couple more generations. I'm going to have 10 generations because I'm going to have something happen at generation 3. Okay. And at generation 3, the environment is going to change. And when this environment changes, it is going to make the environment better suited for individuals of some genotypes and other genotypes. So that's what I'm going to do to for my Hardy-Weinberg, for my mathematical modeling, for my question. Okay, so let me add a couple more generations. I made my populations a little bit bigger. Now I'm gonna, because I really want to be able to see this change and track it for a while. I mean, this is the power of mathematical models. Like, it takes me a couple minutes to get it set up, but once I have it set up, I can do all sorts of crazy stuff to it. Now, here's the other thing. It can be easy to mess this up. And so what I always like to do, I'm going to go up to 10 here real quick. And then I'm going to just copy this whole spreadsheet. And I'm going to make another copy of it. And this way, if I do mess something up really bad, I have my original here. And I didn't mind adding 10 generations and an extra 150 individuals to my spreadsheet. So I waited to make my extra copy until I was done beefing it up. Because right now the changes I've made have just been like adding more stuff to it, not taking anything away. And that's where I started to get nervous. Okay, so I'm going to go down here where it says sheet 1, and I'm going to rename this original. I always like to keep an original, like that this is my raw data. Okay, and now I'm going to make a new sheet. And I'm going to rename this one natural selection. Okay, and so I'm going to go to my original. I'm just going to click in this upper corner here. I'm just going to Control C the whole thing. And I'm going to go over here. I'm going to Control V the whole thing. And then I'm going to hit F9 a handful of times to make sure. Oh gosh, and now it's huge. Okay, and I'm going to hit F9 a couple times to make sure it works. I mean, it looks good, right? Like my P's are around 0.6, my Q's are around 0.4. It's changing every time. I never did spot check my 10th generation. Is that one updating too? I mean, it looks good. It looks solid. I'm a little disappointed that my P's still have so much variability into them. Dang, randomness. Apparently it's a thing. Okay. You know what? I'm not going to use these graphs, so I'm going to delete them because I feel like they just slow everything down. Okay, now the problem, okay, no, never mind. Okay, so I'm going to make it so at the 3rd generation, the environment changes, okay? I'm just going to highlight this whole, after, okay, I'm going to put a highlight in right here. After the 3rd generation, my environment changes, and it changes in such a way that it makes it so all my individuals who are homozygous recessive, half of them die. Okay, so I'm going to kill off half of them. And the easiest way that I've found to mathematically kill off half of them, scrolling down. Okay, right. So right here, I had 39 BB individuals. I'm just going to, let's see. I multiply this by 0.5. Will that kill off half of them? Let's see what happens, right? I'm on my copy of my spreadsheet, so if I mess it up too bad, it's not going to do anything. So I'm just going to add at the end of that equation some AE5 through AE276. Apparently I have 271 individuals in my population. I'm going to multiply that number by 5. Okay. And why did my P get so much smaller? And my Q get so much bigger? Because I multiplied it by 5 instead of 0.5. Huh, okay. Let's try that again, multiplied by 0.5. Okay. F9, F9, F9. So I'm having fewer Q BB individuals, and my Q allele is a little bit smaller. So this change in the environment, it's going to be permanent, and it's going to make it that half of these BB individuals die too, right? Maybe they are fish swimming in a stream, and now the stream has gotten muddy because somebody built a plant that dumps dirty water into the stream. And these BB individuals, maybe their gills don't work as well in dirty water, right? Okay, and I'm gonna, so and the water's still dirty here, okay? So I'm gonna keep going down my spreadsheet and multiplying my number of BBs by 0.5 because half of them are dying. Poor little fishies. Okay, this one right here, take this, multiply this by 0.5. And this is intuitively making sense to me because I would expect my Q to be getting smaller, right? And look at that, it is. Okay, not that time, but all the other times it was getting, wait, what? Why is it? Oh, I did it again. I multiplied by 5 instead of 0.5. Okay, common sense checks. Okay, now it's smaller. Multiply this by 0.5. Multiply by 0.5. Don't forget the point that time. Okay, my Q is still getting smaller. Multiply this by 0.5. And multiply this by 0.5. Okay, so what I have walked you through here is my scientific question. What happens if the environment changes after the third generation in such a way that it cuts down the survival rate of the homozygous genotype individuals by half? That was a mouthful. I think I'll type that up. Okay, so you can see it because I didn't get one. Okay, so on this natural selection, my question is, what happens to the frequency of the P and Q alleles if the environment changes after the third generation in such a way that it makes it so only half of the homozygous recessive BB individuals can survive. It was really long. Okay, and then my method is after generation 3, multiply the number of BB individuals by 0.5. This cuts population in half, which simulates half of them dying. And I just want to add this note that the environmental change is permanent. Whoa, I don't know what's happening with my silver. Oh, it's because it's like centered instead of lefted. Okay, the environmental change is permanent with every subsequent generation of the BBs continue to die. Okay, so that is my question and that is my method. Okay, I think I'm going to stop here. I want you to formulate your question and your method and see if you can get your spreadsheet to do that. If you have any questions, let me know and I'll see what I can do for you. And then in the next video, we'll talk about how to kind of think about a control scenario. There's a couple different ways that we can do that. And we can also think about how we're going to collect and visualize our data, because every time I hit F9 or do anything, my data changes, right? And I can see, oh, wait, before we do that, let's do a hypothesis. Okay, my hypothesis is the frequency of the Q allele in the population will decrease because the number of because some of the individuals carrying that Q allele die, thereby removing their genes from the gene pool. And it's kind of funky. I mean, there's a lot of things that are funky about this, right? It's a mathematical model. So one of my limitations of my mathematical model is I'm keeping my population static every time. So my population is always exactly 271, right? Even when half my BBs die, like my population still goes back to being 271, and it's a little bit smaller here because when I multiply that in half, my population here is only 272. Here it's 262. I'm seeing that when I highlighted that, I do a quick little sum down here. So it's a little bit funky, it's a little bit wonky, but that's okay. I'm doing the best I can with this mathematical model. So there's my question, there's my method, there's my hypothesis, and I can see that my Q is going down as I would expect. But every time I hit F9, it changes. So I can't say if I change my, if I reduce, if half of the BBs die, then Q will become 0.165 because I have F9 and it becomes 0.14, and then it becomes 0.20, and oops, that was F10. I don't know what just happened. Okay, and then it becomes 0.22, and then it becomes 0.15. So it's different every time. So I need to figure out how to take into account this variability in my data. So that's what we'll talk about next time. Okay, so in the meantime, I want to know your question, your method, and your hypothesis. All right. And I hope you are doing well. See you next time.